Hello, in this video we're going to talk about Le Chatelier's principle, which has a bunch of applications in everyday life and in chemical industry and chemical reactions. It's actually something that we use a lot in chemistry, so let's talk about it. So the idea here is that if you have a system at equilibrium and then you subject it to a stress, so you do something to it, it will tend to react in a way that counteracts that stress. It tries to undo the stress. So at an equilibrium, you're looking at the macroscopic properties of a system, be it concentration, pressure, what have you, and they're generally constant, okay, but then you can mess that up. You can change the concentration of a reactant or a product. You can change the volume or pressure of your gas that you're dealing with. You can change the temperature, things like that. These will all affect your equilibrium in some way, and it's really helpful to be able to figure out how that shifts your equilibrium position so that then you can know what happens to your system. And then this last point on the bottom is really important for synthetic chemistry, is that you can perturb the system in such a way that it's going to make more products. And then that's really useful because you have some reaction that didn't make very many products, man. But if you perturb it in a way, you can get it to make a lot more products, and that's useful. Okay, so let's do some examples here. So say you add or remove a reagent. What happens? And this is also true that if you change the partial pressure. If you increase a product or decrease the reactant, what that does is it makes this bigger, right, if you increase the product, or decrease the reactant, it makes less of this. And then that's going to make your Q bigger, so your Q will go up. And then your Q will be bigger than your equilibrium constant, because if you start at equilibrium and then you perturb it away from equilibrium, now you can deal with Q. And then if Q is bigger than K, your reaction is going to go back to the left. So what you did is you added a product, you put products in here, and then your equilibrium position shifted to the left overall. And then it stops after some time, but it still has these shifted concentrations because you perturbed it and then it came to equilibrium again. So you added more products, and then your system shifted to try to make products go away by turning them back into reactants. So it tries to ease the stress on the system. Now the other way around is if you make more reactants or make less products. So I'm going to make more of these, of those, and then that means that's going to make more of this. And if this number on the bottom gets bigger, then Q gets smaller. Now, if Q is smaller than K, because we're no longer at equilibrium, we perturbed it, Q is smaller to K, this thing's going to go forward to the right. And so, all right, so this goes forward to the right. If you add more reactants, it shifts to make less of those reactants and turn them into products. Kind of shifts away from whatever you just did. And this is where it becomes really useful for synthetic chemistry. If you had some magic way to get rid of iodine, so remove a product, then it's going to shift your overall reaction to the right to make more products, and maybe that's useful, right? In this particular example, it's not useful, but say you have some reaction that produces water, and if you basically dry the reaction out as you're running it to get rid of water, it's going to push the reaction farther to the right and make more and more products, which is super useful. All right, stuff also happens when you change the volume or the pressure, and this is specific to the gas phase reactions. And this is the example we'll use. Say you have some simple system that goes between something in 4s and something in 2s, in this case phosphorus. So if you increase the volume, which is the same thing as decreasing pressure because the ideal gas law says so, what you're going to do is it's going to make more gas molecules because effectively you decrease the pressure, so the system is going to shift the equilibrium to try to make more gas molecules. The other way around, right, if you decrease the volume or increase the pressure, well, now your system's going to try to make fewer gas molecules to lower the pressure a little bit, if it has that option, right? And so the reason it does this is because of Q and how it relates to K. So the pressure of the product here is squared in the numerator. So if you increase the pressure, well, that's going to increase the partial pressure of both of these, but it's going to affect your number on top much more because it gives you the square of that change. So then it'll make this bigger. You're going to make Q bigger if you increase the pressure. And all right, Q bigger than K, that means you're going to push your reaction back to the left. And if you push this reaction to the left, then you're taking more gas molecules and turning them into less gas molecules to try to overall decrease the pressure slightly. And it'll do this until it hits equilibrium. Now, one last thing to talk about is what happens when you have a catalyst in. And remember, a catalyst is some substance that increases the rate of the chemical reaction, but is not actually overall consumed. And so say we have this process where you're making ammonia from nitrogen and hydrogen with an iron oxide catalyst. Well, here's your form of the equilibrium constant in terms of pressure. But overall, the catalyst doesn't change the equilibrium composition at all. It just makes it go faster. So it's not going to change really the position. It's going to change both the forward and reverse reactant rates. And it's not going to affect equilibrium. Catalysts are for rates. They're not so much for equilibrium. All right, now it's time for some practice. So say we have this reaction. What happens if you increase the concentration of Al2,6, which is a reactant? You make more reactant. What's going to happen? Well, this is going to shift forward to make more products to try to undo that change. Now, what if you change the pressure? These are both gases, and there's one thing on each side, but overall there's 2 moles of gas on the right and 3 moles of gas on the left. So if you increase the pressure of the system, this thing's going to try to compensate to make less gas molecules, which will then decrease the pressure. So it's going to shift it to the right to make more products. If you do it the other way around, you decrease the pressure, it shifts left. If you have some reaction where you have the same number of moles of gas on both sides, changing the pressure isn't going to do anything because there's not really an advantage there. Okay? And then what happens if we increase the volume? Well, if you increase the volume, assuming other things are constant, you're going to decrease the pressure. Now, then it's the other option here. So you decrease the pressure, so then the system is going to shift left in order to make more molecules of gas to try to counteract that, so then we're shifting to the left and making more reactants. All right, now finally, what if you add a catalyst to this? And well, a catalyst just makes the reaction go faster, but doesn't shift the equilibrium position necessarily. And so we're going to say this stays the same. It doesn't change. So that's Le Chatelier's principle. Again, it's important in a chemical context because if you were to remove a reactant, you could shift your reaction back to the left. That's not so useful. But if you remove a product, that's great. You can shift your reaction to the right, make more products. And all of your biochemical systems in any biological system is in equilibrium all the time. And so if you perturb that equilibrium, you can make more or less of different molecules and take advantage of that. So you can kind of think of equilibria as just being balanced carefully, and you can prod it one way or another depending on what you do to the system. And it's useful to know, and you can take advantage of it. So that's all we have. Thanks for watching.